Okay, let's dive right into this incredibly fascinating explainer. Today we're going to trace a single, highly abstract mathematical concept all the way down to the physical silicon of next-generation AI hardware. Now, if you've been following the massive, rapid scaling of language models lately, you already know we are hitting some serious physical limits. So we are going to look at a radical rethinking of the fundamental geometry that underpins computer processing. We're talking about shifting from infinite points to discrete physical tiles, and how that shift is literally rewriting the rules of metabolic energy in computing.
Right off the bat, this is a multi-billion-dollar question in AI. As our current large language models try to process larger and larger context windows, we're talking millions of tokens now, they are hitting a massive metabolic energy drain. In the industry, this is widely known as the memory wall. But there's actually a much more insidious layer to this problem called the trigger wall. It turns out the fundamental math you use to orient these models in space is just burning through power at a totally unsustainable rate.
To see exactly how we solve this, our agenda today has 4 parts. First, the AI energy bottleneck. Second, Turing cell mereology. Third, algebra versus geometric tessellation. And finally, hardware pruning controllers.
Starting with Section 1, the AI energy bottleneck. Let's look at exactly why our current systems are so power-hungry. The root of this entire energy problem actually lies in a 400-year-old mathematical legacy. Current models use legacy Euclidean space, which relies on continuous polar manifolds. And because they map data to a continuous circle, they require really complex trigonometric calculations, specifically sines and cosines, just to compute attention scores. That right there is what creates the trig wall. In high-velocity inference environments, the cost of these transcendental lookups introduces what's called approximation drift. Basically, because the math relies on infinite points, the system has to constantly guess and round off numbers, which wastes massive amounts of metabolic energy. The solution? We need to move to a discrete rational lattice where calculations are finite, bit-perfect steps. Now, to fix this energy drain, researchers literally had to rebuild the coordinate system from the ground up, using a concept called mereology. Simply put, mereology is the mathematical study of parts and the wholes they form. So instead of using traditional zero-dimensional infinite points on a grid, this new framework replaces them with physical, discrete surface regions called tiles. You aren't calculating an infinitely zooming point anymore, you are calculating a finite, explicitly bounded area.
Which brings us to Section 2, Turing cell mereology, the geometric heart of the solution.
This brings us to a really brilliant concept, the Turing cell. It's a 1-bit state primitive. In this mereological framework, the core unit, which is called D0, is perfectly resolved by its own substates. It creates a physical boundary for computation instead of an infinite point. The larger area is fundamentally constructed by the smaller geometric lenses sitting right above it, creating a completely self-contained geometric cell. Moving to Section 3, algebra versus geometric tessellation. Because the math on a chalkboard doesn't always match physical reality.
Let's put on our auditor hats for a second. If we look at the strict algebra of the silver partition invariant, it's incredibly clear. The math strictly demands one secondary remainder to perfectly close the cell.
But let's spot the difference here. Visually speaking, the pure mathematical D2 is actually spatially distributed into 3 distinct parts to make the physical geometry work. You have these smaller triangle shapes distributed around the inner core. So the pure algebra says 1, but the geometric drawing explicitly shows us 3 distinct spatial regions functioning together as that single mathematical remainder.
To understand why, we have to look at the wider mapping. Why draw it in 3 parts? Well, that 3-part spatial distribution is absolutely necessary to fit the internal cell into the broader kissing tessellation, or perfectly touching pattern of the octagonal boundary. Basically, to tile these shapes perfectly across a 16-phase lattice without any gaps or overlaps, the physical geometry of that D2 remainder has to stretch and distribute itself.
It is so crucial to remember that this Turing cell geometry is an idealized mathematical model. The visual diagrams are spatial distributions meant to stretch and fit the octagonal scaling horizon. Think of this as an idealized map of logic, not an exact wiring schematic for a circuit board. The physical layout absolutely has to flex to fit the tessellation of the plane, but, and this is the magic part, the functional algebraic logic remains strictly bit-perfect.
Section 4, hardware pruning controllers. How does this abstract geometry actually save power?
It saves power because this idealized geometry directly dictates actual hardware pruning controllers. This entire framework is implemented via a global remainder register on the chip. It actively tracks the accumulated metabolic potential of individual AI attention heads. And when the resolution remainder falls below what's called the Hakicity floor, which, by the way, is simply the physical boundary of that D2 remainder we just talked about, the hardware literally tells the chip's halting gate to stop calculating. It triggers a hardware-level pruning strike, instantly bypassing power-heavy SRAM accesses.
By shifting from infinite transcendental math to this discrete, geometry-bounded mereology, the energy required for a scoring operation just completely plummets. Based on 28 nanometer CMOS benchmarks, a standard FP16 multiplication for an attention score takes about 3.7 picojoules. But a reciprocal shift utilizing this discrete lattice geometry, that drops the energy cost all the way down to 0.05 picojoules.
That is a staggering 74 times reduction in energy per scoring operation. Let that sink in. By changing the fundamental coordinate geometry from continuous approximations to finite mereological tiles, we move from an expensive 3.7 picojoules down to a bit-perfect metabolic floor of 0.05. The hardware physically stops consuming power because the math tells it that the finite area has been perfectly resolved. No more guessing.
The real-world impact here is massive. By understanding the nuanced difference between the idealized algebra and the geometric tessellation, engineers can actually build one-bit LLMs that maintain absolute stability over massive context windows, all without burning infinite power. It completely eliminates the trig wall. In empirical tests, while legacy systems exhibited crazy precision drift, this geometric framework maintains zero precision drift across 1,000-step simulations and bit-perfect stability across 128K context windows.
Honestly, this leaves us with a truly fascinating paradigm shift. We have spent decades trying to build smaller, denser, hotter silicon to brute force our way through complex computations. But this Turing cell mereology shows us that the ultimate hardware optimization might not come from better silicon at all. It might come from better pure mathematics. If we can save 74 times the energy just by changing how we draw our coordinate grids, what other massive hardware bottlenecks are waiting to be solved by simply rethinking our fundamental geometry? That is definitely something to chew on. Thanks so much for joining me on this explainer, and I'll catch you in the next one.